Welcome to NucleCast, the official podcast of the ANWA Deterrence Center. Each week, we bring you leading experts for a lively discussion on topics related to strategic nuclear deterrence. Our host is Dr. Adam Lowther, Director of Strategic Programs at the National Strategic Research Institute. The views of the hosts and the guests are their own.
Welcome back to another exciting episode of NucleCast. Of course, I am your host, as always, Adam Lowther, and today we have with us a great guest, Dr. Juan Vitali, who is a nuclear engineer. He's a career Army civil servant, but right now he is spending some time over at the White House as the Associate Director of Nuclear Energy Innovation at the Office of Science and Technology Policy at the White House. And he's helping the administration to advance nuclear energy as one of our clean energy sources. And we were talking before the show, and they're actually doing a lot of really interesting work that I think you, the listeners of NucleCast, you're going to find interesting. And of course, Dr. V, welcome to the show.
Thank you. Very happy to be here with you to talk about my favorite topic.
It's one of our favorite topics too, because many people don't realize this interrelationship between nuclear energy and then nuclear weapons, the defense side, the energy side, the defense side. They go hand in hand. And so, given your background, you've been an Army civil servant, so you clearly understand both sides of this. Let me open the show by asking you, could you perhaps explain for the audience who may be familiar with 3 Mile Island, with these legacy reactors that were built 50 years ago, and may not be familiar with this new generation of nuclear reactors today that are almost like the difference between a Packard and a Tesla. It's just we've come so far over that period. Can you help us to understand what exactly those differences are?
So I'd like to compare it better to a rotary phone and a smartphone. The current fleet of reactors that are being considered advanced reactors are not your grandma's phone, are not your grandma's reactor. And so there have been a number of improvements in safety, passive safety, namely where you have reactors that are physically impossible to melt through. You have high temperature gas-cooled reactors. You have molten salt reactors. We have fast reactors, which produce uranium-235 and plutonium. So they're kind of breeders, but not really. And they're all using high-assay low-enriched uranium, which is not your low-enriched uranium level, which is about 4.5%. It's more of the 19.75%, which is the threshold for considering something to be a proliferation risk. It's considered to be anything below 20% is appropriate for nuclear power. So it's a reactor design that has all the characteristics. So there's a number of different designs that meet this characteristic of being generation 4. 3 Mile Island would not pass current safety, wouldn't exceed, let's put it this way, the passive safety standards that we have now with generation 4 reactors. And so we see that as a great selling point for these reactors in terms of safety, in terms of life cycle cost, in terms of the size of the reactor, in terms of all the different aspects that lead to life cycle economies that are better for different applications that we consider in the military, but also in the civilian sector, right? So we talk about SMRs, so small modular reactors. We also talk about microreactors, and the distinction there is microreactors are small, anywhere from 10 to 20 megawatts and less. And then, of course, small modular reactors, by definition, are those that are 300 megawatts or so. reactor power output. So we're dealing with a bunch of these designs. DOE is doing a wonderful job with the ARDP program, which is the Advanced Reactor Development Program. There's a dozen designs being funded by DOE to create a prototype by sometimes the year 2030, 2033. Out of those designs, there will be a number of them that will be successful in a timely way. And then I think they're really driving fast to move the needle on decarbonization. In the military, we have this great project called Project Pele, which is a microreactor, and it puts out about 1.5, 2 megawatts of power, and it's also considered transportable. And that's the real difference between the civilian purpose and the military purpose. We see the Pele as meeting a number of mission requirements in far-flung places, places like Alaska, where you have very remote areas where you have military operations, whether it be troops or whether it be radar sites, missile defense sites. And the same type of environment, but less cold, I should say, is Indo-PACOM, which has requirements for fuel and electricity. And this Project Pele is kind of the enabling for this particular set of missions. So Project Pele, again, is a gas-cooled reactor, which also is transportable. And we're aiming for that reactor also to provide not just electricity at a moment's notice, but also the ability to synthesize fuel. There are a number of projects within the the Air Force and the Navy who have demonstrated the ability to capture carbon and also use that carbon to make synthetic fuel that is able to be used by, our jets.
So we're going to be able to take, this is something I haven't heard about before in terms of Project Pele. We're going to be able to actually capture carbon and turn it into fuel. So if we're at a remote base, we've got a fob somewhere, or maybe we have helos, and we can literally create fuel for those from that reactor. Yes. Wow, I had not heard that.
Yeah, that's right. There's a company in New York, in Brooklyn, called AIR, just like that, AIR. And their mission, funded by DIU, Defense Innovation Unit, to produce a Conex-sized system that can synthesize jet fuel, whether it be JP8, diesel, or what have you. It's fantastic. It's not just about capturing carbon, but also doing the electrolysis, splitting of the water molecule to put together and to create polymers and make the fuel for aircraft alongside the lubricants and all the rest of it. So it's really exciting stuff. And then, so the impact of that is to deal with the issue of contested logistics, right? So as we see, our future conflict sites in the Pacific, potential conflict sites, we have what used to be a main advantage for American power, which was our ability to resupply our front lines. I mean, that's been the key to our successes in war making and war in general is our ability to resupply our front lines and continue the fight. That is enabled by a great combatant command called Transcom, which you can't, and it's currently using basically ships to send diesel to all these locations. And so our supply lines have become more vulnerable because of our adversaries in the area have gotten the ability to produce long-range precision fires, which inherently become very powerful and for which we need to defend against. And so our supply lines need to be protected, or at least reduce our dependence on long supply lines that could be vulnerable to attack. So therefore, any and all technologies that allow us to reduce our dependence on fuel and whether it be to provide fuel for aircraft or provide fuel for electric supply in the different locations around the Pacific or Alaska or elsewhere. That is one of the big goals of today's military. So whether it be the Joint Staff, the Army Futures Command, the Air Force, everybody's geared towards solving this big problem, which is contested logistics.
Yeah, now that you mention it, it sort of has me thinking about the fact that if we could reduce the fuel requirements, like you said, through these, Project Pele and these other reactors, that if let's say we have troops that are deployed and they're not requiring fuel that has to then be shipped to them, they instead have reactors. Or and I think before the show you had mentioned the commercial shipping. So if you think about all of the, the support ships, I was a sailor on destroyers and frigates, and we would have to do underway replenishments and we would take on fuel. And if you could sort of somehow through this logistics line, this contested logistics line, reduce the amount of fuel that ships take on, you could dramatically reduce the amount of replenishment requirements. There's just so much potential to decrease the number of targets for an adversary to strike to interrupt the American logistics trail. So it's amazing, and it's something I hadn't thought about before. And now that you mention it, it's really quite something.
To keep being realistic about this. So the electricity being produced by diesel is by no means the largest use of fuel. The largest use of fuel is aircraft, and it has been that for the two most recent operations in Iraq and Afghanistan. It not always has been where aircraft consume the most amount of fuel. So all this does is, at the very first stage of this deployment is replace the diesel that goes into electric generation. But the second most important thing is using this new technology to produce jet fuel, which really would consider to be game changing in the battlefield.
And do you see this these fourth generation reactors, some of the projects that are underway the Army has, as being almost, I've seen, for example, where Tesla, the batteries, for example, are so expensive that, once you have to replace the batteries, you just get rid of the car. And there have been some there's some guys on YouTube that have taken the batteries out, and they're building engines, gasoline engines that are now put in the Teslas. So could you sort of do that in reverse where, I was on an Arleigh destroyer, which has two essentially jet engines, gas turbines. Could you sort of pull those out and put one of these reactors in and replace that requirement for, because we would have to, when you're burning fuel on a ship because you've got a gas turbine engine, you're burning through lots of diesel fuel or lots of jet fuel. And could you replace it with a reactor and eliminate that requirement?
So there's two options to that, right? There's reactor producing electricity that moves a shaft, and or have the reactor itself become an electricity generation system that moves a shaft, whether it's direct conversion of steam, heat energy into mechanical energy, or producing electricity in between. Those are two different spaces that we can consider. So that could be an option. Certainly, the Navy does both of those things. So certainly that. But I think again, so going back to the biggest need is aircraft fuel.
Sure.
That's the more like 2/3 of the demand signal and the conflicts that we saw recently, and logically so. So
now you've in working this project at the White House, you've clearly seen that regulation needs to change to make nuclear energy a viable source of clean energy and for some of these broader purposes. What do we need to do to make, because it's really expensive and difficult to build a new nuclear power plant. What do we do?
So let's make a distinction. Project Pele is a military reactor which operates under right now under the auspices of a DOE regulation to build it in Idaho for testing purposes. So that's one piece. Once it becomes an official piece of equipment for the DOD, there's a whole bunch of different regulations that apply only to DOD, where the NRC doesn't necessarily have input into that. So if we grab that and deploy it in DOD, we have a certain set of regulations that are independent of the NRC. Now, the other piece to this, that was my job at the Army before I came to the White House. I'm still working the pieces of that in the Pentagon, but I'm also working out different aspects of nuclear deployment. So one of the big things that we're looking at is all these advanced reactors for which there hasn't been any regulatory work actively by the NRC. They require special type of understanding of how these systems work. But beyond that, there have been numerous occasions where the licensing of these reactors, any reactors, but most recently Vogtle in Georgia, stumble upon a number of issues, and also other reactors relating to their deployment. Sometimes it takes too long. NuScale, which is a new advanced reactor, Gen 3 reactor, took more than was expected, 3 to 4 years to get it licensed. So if we're going to meet the moment with regards to energy resilience, energy decarbonization, and addressing these issues of global warming, more primarily to address the demand for energy as it's continuing to grow across the civilian space, we need to meet the moment and accelerate our ability while maintaining safety, because that's important, right? So that's very important. We don't skip on safety, but we also want to accelerate our deployment and our licensing procedures. So we're beginning in the early stages of engagement. I would like to see more engagement from industry and others to make sure that we can go faster on how we do a regulating and a licensing. And so again, we're at the early stages of this process, but there's a clear need to accelerate our ability to license proper reactors.
Now we're at that time. Oh, sorry. Go ahead.
Go ahead.
Well, we're at that time in the show where we have to take a quick break. So when we come back, I want to ask you to explain to the audience. So there's this discussion about putting reactors in the field, on the battlefield. And people naturally have safety concerns. When we come back from the break, could you explain how we would do this safely? You're listening to NucleCast, and we'll be right back. This episode of NucleCast is brought to you by the AMWA Deterrence Center, whose mission is to educate Americans about the nuclear enterprise and strategic deterrence. And we're back, and we're talking to Dr. V about safety of Project Pele and other reactors on the battlefield. So for the listeners, how do we do this safely?
So we, the designers and the folks at OSD never intended for this reactor to be what we call a closed area, right? Or the battlefield at the edge of the fight. We see this reactor as enabling this is the strategic support area, which is many clicks away from the front. And so what that enables is, aside from the electricity to provide electricity for lighting and so forth, but also provides electricity for APODs, SPODs in the strategic support area, medical facilities, additive manufacturing, and a sundry list of applications that are all in the rear, so to speak, in the strategic support area. And we think that is very much an enabler. So it decreases our ability, it doesn't decrease our ability, it enhances our ability to push that fuel that would go to normally to electrical diesel generation to the more requiring the more intense use, which is aircraft fuel. So we are basically replacing roughly with the current payload reactor, roughly 2 million gallons of fuel with the payload generator. It's designed to be a HALO system with 3 years of continuous operation at 100% capacity. If you run it at 50% capacity, it will last you 6 years, and so on and so forth. Think of it as a battery, if you will, a nuclear battery. But so the answer to the question is, well, first of all, we're not putting it under direct live fire contested space. We're putting it in the rear. Second, if we are thinking of the risk assessment of what would happen to a reactor in a battlefield if it gets hit, well, I would sort of first say the diesel generation systems require these humongous fuel farms that have a center air probe of hundreds of yards to store and supply fuel in that strategic support area. So, and the footprint of that compared to the footprint of Project Pele is almost a ratio of 10 to 1. So you have a bigger target by hitting a fuel farm than having a tiny little reactor in that sense. So bottom line is, if the reactor is hit, it's a mess. We will not sugarcoat that. But the advantages that come from assessing that risk, that is of a reactor being placed in the rear, protected by air missile defense and protected by all kinds of capabilities, is worth the risk given the advantage and the capabilities it provides to the rear. And I think that's what we heard from a number of combatant commands. They really want this very quickly, and in areas where we can't use, our supply lines are continuously contested. I think those are really good reasons to adopt nuclear power. So a lot of demand signals on this, and General Flynn in the Pacific has enthusiastically told us that he'd like to see this capability sooner the better. So we see this as a non-issue. I mean, obviously it's an issue if you get hit, and so we have our ability to describe what happens when it's hit. So we estimate the emergency planning zone to be no more than 100 meters in that case. So which is a capability risk. So
yeah, I mean, when you say 100 meters, that's pretty tight. That's actually not a significant.
And by virtue of the fuel, right? TRISO is a tiny little pellet the size of a poppy seed, and you use this fuel in these reactors. And the thing about that fuel is that if you hit and these tiny little pebble beads go all over the place, they don't go any further. And so because they're so tiny, they don't have very much to go, very far to go.
So we were discussing before the show some new uses for these nuclear reactors that I had just never heard of. I didn't know they could be used in these sort of new and innovative ways. I'd always thought, we generate power. And you've talked about, we're going to generate jet fuel with them, and you've listed, we were talking, you mentioned some other areas. Could you explain for our listeners what are some of these unique areas where we can use these new reactors?
Yeah, sure. So one of the big things, in the military sense, is trying to enable additive manufacturing, right? These large facilities, so that we can manufacture parts in the battlefield or in the strategic support area more precisely, and not having again to provide long supply chains of these different parts for the repair and maintenance of our fleet, whatever it is. That's one application. The other one is, again, thinking of the Pacific, is desalination. I think it's again another huge impact on contested logistics. Water and fuel are the biggest signals for class 3 and others to transport for long distances. So the amount of potable water that we have to ship to support the battlefield is enormous. So I think our ability to grab seawater and desalinate it and provide it in sight, that's another big plus. Another one is, now talking about the civilian applications, is to provide hydrogen to make steel, decarbonized steel. So that's another one. Or even providing hydrogen for different things. People are talking about making hydrogen available for transportation of car fueling with hydrogen and other things like that require hydrogen. Another one, good use, is we saw it in very much alive, is this issue of fertilizer production, which Ukraine, being hit by the Russian invasion, had to curtail the amount of fertilizer that was being produced, which had a ripple effect across the world economy, right? Because as soon as you decrease the supply of fertilizer, all of a sudden now your crops yield less, and because they yield less, it has an inflationary impact on the world economy. Interesting how just a little bit of fertilizer price check and price increase causes all these pieces of economic impacts across the board. So we want to see our ability to make hydrogen on site and replace the traditionally used natural gas to produce fertilizer. Besides that, we're talking about I talked about additive manufacturing, food manufacturing. That's another one. It requires a lot of energy, and so again, providing the ability to provide energy to make to synthesize fuel is another one. So there's about half a dozen or so applications that we see, case studies that we're actually promoting and studying to enable, so that nuclear energy becomes the enabler for all these different applications, reducing cost, reducing logistics, and making things more inexpensive for the public in many ways, and enabling the military to achieve mission. Yes.
Now we're getting close to the end of the show, and at this point in the show, I like to bring out my magic lamp, and I started to let guests make 3 wishes, so I'm going to let you rub that lamp, and you've got 3 wishes. What would those 3 wishes be in regards to this issue of nuclear reactors, nuclear energy? You can do anything. You've got 3 wishes. What are they?
I would say have an order book of, 200 reactors by next year, whether it be molten-salt or NuScale or, even thorium reactors, if we think about them.
So
too.
This would be, folks, power companies ordering them. So this order book, who would order?
So I would say, the military would be our first place because that's where we have ability to influence the budget. But also, the other spaces, we're making cogent and savvy investments in these technologies. I think there's, like, for example, Dow Chemical engaged with X Energy, and X Energy is building a reactor in Houston or near Houston somewhere that makes use of just the steam, not even the electricity, to make chemicals by Dow. So those kinds of deals are going to be more and more coming forward. There are another one which is interesting, is we talked about earlier, is the maritime piece, to build these long haul ships that are extremely dirty in terms of their pollution creating by using not diesel fuel but crude oil. I forget now what the combination is, but very, very polluting. There's an opportunity there to not only create this new capability, but to restart the shipping industry, which has been pretty much dying the last 40, 50 years. And where Japan and Japan, South Korea, and some places in Europe have taken the lead, and the United States, which used to be one of the biggest shipbuilders in the world, has virtually come to a halt in producing, unless you're talking about military uses, which is completely different. So
that's your.
I like to see that. That's low-hanging fruit, because that we already have companies doing that, and INL in the Idaho National Laboratory is helping put together the TerraPower derivative for companies to do this maritime nuclear. So that's a low-hanging fruit. I like to see that.
And you've got one final wish. What is that final wish?
My final wish is to have one or several plants that produce uranium. Not produce it, but refine the uranium, produce TRISO. That's a capability that we're missing. But we're heading in that direction. I think companies like Centrus are taking the lead with some help from the government to produce uranium, high assay, low enriched uranium. So there you go. They have three of our wishes.
Well, this has been an interesting show. So you really brought a lot new to think about for me and for the listeners. So we appreciate you doing that. Dr. V, Juan Vitali, thanks for coming on NucleCast.
Thank you very much for having me.
And thanks to the listeners, and we will see you on the next episode of NucleCast. Wow, that was interesting. I don't think I had thought about the logistics component is something, how nuclear reactors can affect logistics and how we can take advantage of that. That's something I had not thought about. And then some of these additional uses for reactors. That's also something I hadn't thought about. I mean, we really didn't get into a discussion of just how reactors are part of, anybody's desire for clean energy, because, you can't build enough wind farms and solar to make that happen. You got to have nuclear. That, I think, a lot of people sort of understand. But some of these military applications are beyond anything. I knew we could power FOBs, and we could move these out to forward locations, but some of these other things, man, that was interesting. Hopefully you found that interesting too.
This has been a production of the ANWA Deterrence Center. Our executive producer is Kimberly Charrington, and this episode has been engineered and mixed by David Krumthal. Follow the show on LinkedIn, Facebook, and Twitter at NucleCast. Listen, follow, and review the show on Spotify, Apple Podcasts, Amazon Music, or wherever you listen to your favorite podcasts.